Okay, good morning, ladies and gentlemen. I would like to say thank you for coming in my presentation. It's great to see you all. Let me introduce myself and my team. My name is Laila Fauziyah Aminni, and my team is Mrs. Widyaningsih and Mrs. Saputro. We are from Department of Mathematics, Faculty of Mathematics and Natural Science, Sebelas Maret University, Indonesia. Here I will present our research entitled measles-free prediction and control strategy to achieve measles elimination target in Indonesia based on SVEIR model. For the first is introduction. The phenomenon of the spread of infectious disease has occurred in various countries. The spread is characterized by the number of individuals infected with the disease. Mathematical models have been widely used by researchers in the development of science and in handling problems. Mathematical models are an important tool in analyzing the spread of infectious disease. In 2000, Hazard formulated a SVEIR model. The population was classified into three groups, namely Group S or susceptible, which is a group of individuals who are healthy but vulnerable. Then the group of individuals who are infected with the disease and may transmit the disease or infected by, and a group of cured individuals or recovered are. The vaccination programs are carried out in the context of preventing and controlling infectious disease. In the 2008, Liu et al. With a SVEIR model. With regard to vaccination, individuals who have received the vaccine are classified into a separate group, namely vaccinated V. According to the World Health Organization statement, surveillance is a very important activity to monitor the progress of programs aimed at disease control and elimination. Surveillance begins by detecting, then investigating and confirming every suspected case in the community. The world targets to eliminate measles by 2030. Based on data report to World Health Organization, in 2019, there were still 1,822 individuals infected with measles in Indonesia. Taking into account the surveillance activities, suspected individuals are classified in separate groups. Suspected individuals have shown or exposed symptoms of a disease, but it is not known whether the individual is infected with the disease or not. Therefore, the suspected individual is classified as an exposed group or E. In this study, we formulate the susceptible, vaccinated, exposed, infected, recovered, or SVEIR model on the spread of infectious disease. So far, the SVEIR model has been formulated by several researchers. Here, the SVEIR model construct in this study is different from the studies. Population is assumed to be non-constant, and migration factors are not considered. Individuals who have recovered are assumed to have acquired permanent immunity. In addition, it is possible for individual E to become S because here individual E is a suspect. Individual who, if not declared infected, may be susceptible to the disease. Then the SVEIR model was applied to measles case in Indonesia. The goals of this study are first, formulate the SVEIR model on the spread of infectious disease. And the second, apply the model to measles case in Indonesia and determine the pattern of distribution and prediction of a measles-free in Indonesia. Then third, simulating the parameters of the SVEIR model to determine the control strategy. The next is SVEIR model. The SVEIR model was first introduced by Kermack and McKendrick in 1927, then grew by Hirsute in 2000. Migration factor is not considered, so that in his study, the number of births is assumed to be equal to the number of deaths, so that the population is constant at n. And then also assume that recovered individuals get permanent immunity. The population dynamics of the SVEIR model is as follows, and it is written as the system 1, where mu is birth or death rate, beta is contact rate, and gamma is cure rate. In this part, the SVEIR model will be formulated by using the SVEIR model as basis. In the SVEIR model, the population was assumed constant. However, here, the population was assumed to be not constant. This assumption have an impact on the birth rate and death rate in the model. The birth rate and death rate are not the same, so that the notation of the birth rate in the SVEIR model is changed to theta. Vaccination program is one of the efforts to prevent the spread of infectious disease. Therefore, taking into account the vaccination program, the individuals receiving the vaccine are classified into group V individuals. Vaccination is given to individuals who are susceptible to the disease. If the vaccination rate is denoted as alpha, then the number of individuals vaccinated is alpha S. Thus, the number of S individuals decreased by alpha S, and the number of V individuals increases by alpha S. The number of V individuals who are successful acquired immunity is increased by the effectiveness of the vaccine. Individuals who were vaccinated and succeed in obtaining immunity become R individuals. This is different. This is different from the SVEIR model of Maret et al. And Adiwali et al. Because in both of them, there is no individual V that becomes R. If the effectiveness of the vaccine is denoted as lambda, then the number of individuals who are vaccinated and successfully acquired immunity is lambda V. Then the number of individuals V decreased by lambda V, and the number of individuals R increased by lambda V. Individuals who are vaccinated and fail to regain immunity become susceptible individuals because it is possible to contract the disease and not have immunity. If the vaccine failure is 1 minus lambda, the number of V individuals who fail to get immunity is 1 minus lambda V. This means that the number of V individuals decreases by 1 minus lambda V, and the number of S individuals increases by 1 minus lambda V. The number of V individuals is also affected to natural mortality. The number of individuals V who experience natural death was mu V. Based on surveillance activity in this study, the suspected individuals were classified into a spared group, namely exposed E. In the population, individuals who come into contact with individual I and do not have immunity can contract the disease. Individual S doesn't have immunity, so it is possible to contract the disease through such contact and become a suspect. If the contact rate is denoted as beta, then the number of susceptible individuals that become suspected is beta SI over N. Referring to the research of Liu et al., individuals who have received the vaccine do not immediately get immunity to the disease, but need time to achieve permanent immunity. During the process of achievement immunity, it is possible to come into contact with infected individuals so that individuals who have received vaccine may be infected with the disease because they have not yet attained immunity. If the rate of vaccinated becoming suspected is denoted as sigma, then the number of individuals vaccinated who suspected is sigma beta VI over N, and the number of V decreased by sigma beta VI over N, and the number of individuals E increased by sigma beta VI over N. If the rate of suspected individuals becoming infected is denoted as eta, then the number of suspected individuals who are declared infected is eta E. Suspected individuals who are declared uninfected are assumed to be susceptible because it is possible to contract the disease after being declared uninfected. This differs from the SVEIR model of Maret et al. And Adiwali et al. Because in both of them there are no E individuals who become susceptible. If P presents the rate of suspect individuals who are declared uninfected become susceptible, then the number of suspected individuals who are declared uninfected is PE. The number of E individuals decreases by PE, and the number of S individuals increases by PE. The number of E individuals is also affected by natural mortality. It is contract to headshot. In this study, death due to disease infection is considered. If delta represents the rate of death caused by disease, the number of individuals I who die from the disease is delta I. The SVEIR model on the spread of infectious disease is obtained, which is written as system 2 with parameter as follows. The SVEIR model was applied to measles case in Indonesia. SVEIR model parameter values were estimated based on measles data. The data used to estimate parameters are annual data in 2011 to 2018. Search from the Indonesian Ministry of Health's Data and Information Center, World Health Organization, and World Bank. The estimation results are shown in Table 1. Based on CDC information, measles vaccine efficacy is 98%, so that the value of lambda is 0.98. The estimation result in Table 1 were substituted in the SVEIR model. Thus, the SVEIR model on the spread of measles in Indonesia is system 3. The model was given initial values to determine the solution. The year 2011 was the beginning of observation on the spread of measles in Indonesia. Therefore, the number of individuals SVEIR in 2011 were used as initial values of the model. The solution was determined numerically by fourth-order Rangkata method. The 2019 data were used to measure the accuracy of the SVEIR model in presenting the spread of measles in Indonesia. The numerical solution in 2019 compared to the estimated number of individuals in each group in 2019. From this, relative error norm from the numerical solution is 1.781519. With the SVEIR model, which has the relative error norm, the numerical solution for 2011 until 2050 is represented in the following graphs. The number of S individuals decreased until 2043 and then increased. The number of V individuals the same but decreased until 2044 and then increased. The number of E and I individuals always decreased until 2046 by 0 individuals. The number of R individuals always increased. Thus, the pattern of measles spread in Indonesia based on SVEIR and measles data for 2011 and 2019 shows that the number of individuals S, V, E, and I are downtrend, while the number of individuals R is uptrend. Based on figure 1C, it can be seen that there are still 196 measles sufferers in 2030. This means that using the SVEIR model and data from 2011 until 2019, the target for measles elimination in Indonesia by 2030 has not been achieved. Indonesia was predicted to be free of measles in 2046 with no individuals suffering from measles that year. The next is parameter simulation. Simulation were carried out on the parameters of contact rate or beta and the vaccination rate or alpha. The simulation result of beta and alpha are shown in table 2. From the result, we can see that if the control strategy is simply to prevent contact, that is, without vaccination, the measles elimination target by 2030 can be achieved by reducing contact by 71% with sufferers. This is no-cost strategy. If an increase in vaccination coverage is also carried out, the target can be achieved by reducing contact by 67% with sufferers, and increasing measles vaccination coverage by 8%, or the reducing contact by 65% with sufferers, and increasing measles vaccination coverage by 36%. In those strategies, costs may be required for vaccination. From this work, we can conclude that first, the SVEIR model on the spread of infectious disease is as system 2. The second, using the model 2 and measles data for 2011 and 2019, there were obtained the SVEIR model on the spread of measles in Indonesia is system 3 with 2019 data. The relative error norm for the numerical solution is 1.781519. B. The spread pattern of measles in Indonesia shows that the number of SVI and E individuals are downtrend, while R individuals is uptrend. The target for measles elimination in Indonesia by 2030 has not been achieved, and it is predicted that Indonesia will be free of measles in 2046. The third, if the control strategy is only to avoid contact, the measles elimination target by 2030 can be achieved by reducing contact by 71% with SVEIR. If with increasing measles vaccination coverage, the target can be achieved by reducing contact by 67% with SVEIR and increasing measles vaccination coverage by 8%, or reducing contact by 65% with SVEIR and increasing measles vaccination coverage by 36. I think that's all. Thank you for your attention. If there are any questions, please ask in the comments column. Thank you.